we just saw that if we pick up an infinitely long plate, the field lines are independent of distance. Based on that, we have the next derivation. We have a derivation wherein we are picking up two such plates, but of course with different density. The funda is that we will take the fact that we know how a single large plate would behave when kept alone. So the field lines are radiating outwards and the strength is independent of distance. Again, if you're not seeing this derivation, please do. If not, you will not understand. Now, the actual derivation starts off in this way. We have two plates, remember. We have two thin, plain, parallel sheet of charges with uniform charge density of sigma 1, sigma 2, where sigma 1 is greater than sigma 2 and both are greater than 0. That is, both are positive charge and their density is fixed, is uniform for that particular sheet. That is, it will be sigma 1 over here, it is sigma 2 over here. Okay guys, now how can we study about this? We know that the field lines are uniform and all of that for an infinite long distance. So how can we make use of that fact and study this? Yes, with the help of super what? Correct, superposition theorem. Actually, we are studying everything based on this only. We'll make use of it again. So we are looking at three different space. One is over here, second is over here, and third is over here. Right? So we have three different place scenarios that we have to consider. Why three different places? Think about it. It's kind of common sense. Because we have the plates at different push and pull scenario in three different places. What I mean is over here, the electrical field line because of rho 1, if it's something like this, over here, it'll be the same magnitude because of this fact, but different direction. Same magnitude over here too, but in a direction different than the first one. While it comes to your second, this is lesser charge density, so the field length will be a bit shorter, but the directions will be different. So here the direction is away, away, and this is also actually everything is away, but to the left and right, yeah. And that's why we need to look into three different cases. Does it make sense? If you guys understand this, you are pretty much done. Okay. So this is the electrical field by sheet 1, sheet 1, and sheet 1. And this is by sheet 2. Because it's same, so in terms of magnitude, it'll remain the same. Actually, this will be opposite now. In terms of magnitude, all of this have the same one. Now, we need a reference direction so as to handle all of this. So we are considering that r cap, a unit vector pointing from sheet 1 to sheet 2. So with respect to this, we can handle these three different cases. It will be basically addition, subtraction and stuff. So yeah. Now, we'll start off with case region first. So here the field lines are in the same direction. Here the field lines from both plates, both sheets in our case, are in same direction. Therefore, the total field will be equal to how much? Sum of those two. And we know that it would be, how much is that? No, rho 1 by 2 epsilon naught. Is it not? And sorry, not rho 1, sigma 2 by 2 epsilon naught. But with respect to your unit vector, it's in opposite direction. With a reference vector, this is in opposite direction, so it will be negative. Agree? So we can take out common and have a final expression minus 1 by 2 epsilon naught sigma 1 plus sigma 2. Now, same stuff. Case region second. In region second, what is happening? A push and a pull. Basically opposite side. Same funda. Here the field lines are anti-parallel to each other. Therefore, I'll call this as first and second. It would be what? It would be sigma by 2 pi epsilon naught minus, here it would be, it's minus, right? This is to the right, so that is, this is plus and this is minus. Okay. This is negative and that is positive, and both are with respect to r cap. And here too we can pick up the common minus sigma to r cap. And finally, this would be same as, third would be same as, like literally same, is it not? There's now no difference. I can just do this. And this, and this. And oh yeah, over here too. Done. Okay. That's it. So what can you conclude? If we have rho 1, sigma 2 to be equal in the region in the middle of the plate, that is, the electrical field lines are 0. While outside those spaces, they will add up and there will be 2 times of E basically. That's one thing that we can do. Quite simple. We saw that plates are, infinitely big plates are, they behave in such a way that they are independent of distance. So E at one place will be the E at the other place also. In terms of magnitude, they'll be the same. Now we have two different plates of different charge density producing, of course, different electrical field. The direction of electrical field has to be perpendicular to the surface, but because the plates are not along the same plane per se, they're parallel to each other and they have a distance between them, we are looking at this particular 3 different scenarios. And they are quite simple. We just have to make use of superposition theorem and we are done. I missed out r cap over here. And so it would be so here as well. Okay, so that's it. So you can pause and have a look.